Hi, this is Nikolai, and my co-host is Michael. Hi, Michael.
Hello, Nikolai.
And this is Postgres FM, and today we talk about memory management, shared buffers, workmem, effective cache size, maintenance workmem, auto vacuum workmem, and so on, right?
Yeah, absolutely. And just before the show, actually, you were telling me you had a joke about this.
I forgot it.
Yeah, nice.
Yeah.
Little double act for you.
So yeah, let's try to be shallow because it's easier, but very wide. I mean, we will try to cover as wide as possible in half an hour, and we can give tips where to. If people want to dive deeper, we can recommend some great materials, great resources such as articles, books, and so on, source code. So where do you want to start? This is your usual question. I'm returning back to you.
I like it. I think you're right. I think the show notes for this are going to be very helpful for people. I think there's going to be a lot of links to things to learn more. But I do think there's a good half an hour in this in terms of high-level things. A lot of the time, I think my experience is very biased because I make a tool for optimizing individual queries. So these system-wide things don't come up as often in the conversations that I'm having. But my understanding is that a lot of people still don't, and there seems to still be disagreement in the community about what is a sensible setting for things like shared buffers, what is a sensible setting for things like workmem. So some of these extremely high level but extremely important settings have some debate around them, and very experienced people disagreeing with exactly what the doc should say or exactly what equation to use to set these, and there seems to be some like differences of opinion from theory, like people more into theory versus people more in practice. Very different. If there's depending on the database, like how big or small it is can make a huge difference to what the advice should be. So yeah, I think there's a good high level overview we can do. So I'd probably like to start with maybe shared buffers. Feels like there's a few things that Postgres uses shared memory for, but that's the biggest, right? Or normally the biggest.
Right.
Do you want to start
Let's
there?
talk about it. Yeah. First of all, let's promise to our audience to use good links in show notes with raw links, because it helps sometimes. Like, for example, other shows I watch, I don't have time to watch the whole thing, and I just want to see resources like blog posts and so on. And if it's behind HTML and I don't see the domain name, it's not helpful. I want to see the domain name and to know who wrote it, like, for example, Cybertech or, I don't know, EDB and so on. Because I have my preferences and I would like to see domain names. So let's promise to use raw links in show notes. But in YouTube, we are forced to do so it's quite obvious. So if you don't want to listen whole episode, just check show notes. It has good set of links. Then shared buffers. Yeah, I agree. This is probably number one in terms of memory management to consider. But there is also underlying thing that we probably should go before it. And underlying thing is called page cache or operational system file cache. So Postgres always works through it. Postgres never reads files from disk, from file system. It always goes through page cache. So the first cache. Well, first of all, why cache? Why do we need cache? Because SSD is quite fast, right? It's like you can do a lot of operations per second. Latency is quite good, like sometimes below 1 millisecond. It's quite good. Of course, memory is much better, definitely. So, of course, we still, despite of the rise of new external storage devices, and NVMe is quite good, and so on, we still need, memory is still several orders of magnitude faster. So, and we have a lot of memory lately. Like you can easily have a server with hundreds of gigabytes and sometimes already terabytes of memory. And memory is super fast. and of course it makes sense to keep a lot of data in memory, so final latency of query execution is better for our end users. Well, our end users are not end users of systems we usually use. Our end users from database perspective are some application nodes or sometimes humans, but very often not humans. So, and we want, of course, query execution to be very fast. Performance is critical for databases, so that's why we want cache. And we always have page cache underlying before even going to shared buffers. We have it. And usually when we think about it, we don't know how much it will be originally, because like Linux, for example, Linux uses for page cache everything it has, which is not used by others, right? All free memory becomes like our page cache memory. And this is good, this is fully transparent. And only then we have the buffer pool, which is controlled by shared buffers, and it's allocated at startup time. So, and it cannot be changed during, while we run server, and this is a big limitation Postgres has. With one of the biggest items I would like to be changed in Postgres, but it's very hard. I mean, it would be great to change shared buffers without restart, but right now it's not possible. So if you want to adjust shared buffers, the size of the buffer pool, you need to restart your Postgres. And since it's allocated, we need to think how big should it be. But thinking about it, we should consider underlying cache, the page cache. So Postgres basically has two levels of cache, page cache and buffer pool. And the rule of thumb right now, 25%. I remember when we started to have more than a couple of gigabytes of memory on most machines, there was a debate, like at some point the rule was 25 if it doesn't exceed like 8 gigabytes, but now it's okay to allocate 100, 200 gigabytes, and it's normal. And I should notice that 25% is not optimal. If, depending on your workload, you probably want to allocate 80%, for example, but it's risky. Like, of course, like I would like to allocate like 90% to shared buffers. Linux would use less memory for the page cache, but it's okay because shared buffers is smarter than page cache. For example, in some cases, Postgres decides to use very limited area of shared buffers. For example, if you perform sequential scan on a large table, page cache doesn't know that it's a sequential scan. Linux doesn't know it. And it will spam your cache, page cache. It will spam it. But buffer pool, you will have a ring, so only limited area, I don't remember, 256K, I don't remember. So basically this process will use only limited area to read whole table, and it won't it won't cause eviction of useful data that is needed by other backends, right? And so buffer pool is smarter than page cache, so we would allocate to 80 or 90%, but it's risky because we can hit out of memory state sooner if we do it.
There's a few, so lots to go on. I think 25% does seem to be, I think it's even mentioned in the Postgres docs. It's mentioned in a lot of guides. As you say though, it's interesting. You say it's not optimal, but like it may not be. Like there probably is a workload. Like if, for example, your tables and indexes are almost exactly about 25% of your RAM, like if they fit exactly in shared buffers, maybe that is an But I'm just saying, like there is possibly.
Yeah. I agree.
But the problem is, it's 25% is likely way better. Well, I don't know. Actually, I hate making statements like this. The problems we've got are that the default is so low that it's unlikely to be a good starting point. 25% probably gives you a better starting point for experimentation, but then to experiment, you need restarts, and you also need to be able to replay your workload and things like that. So it's a tricky. Yeah. tricky one. And before we move on, though, I did really want to say there's a really good tweet from Andres Freund that I couldn't believe he managed to summarize this in basically 2 tweets. But the reason that your statement is a good one, that is probably not optimal, is that assuming your data doesn't fit in RAM, which is like a lot of people, it will. A lot of people, if you're working on a small database, your data might well fit in less than 25% of RAM, in which case you're probably going to be fine. It's probably going to be
Or it's
like
10% of, yeah.
Yeah, exactly. But the people that are going to have problems with this, the people that are going to need to listen to this or look into some of these links, are probably people that have got much larger data sets than will fit easily into RAM, or at least it would be extremely expensive to get a server where they would fit into RAM. And then you've got the problem of the Postgres, the shared buffers, the Postgres cache versus the operating system cache. And I think Andres does a great job of simplifying the fact that you can have it saved in both. And if you have the same data duplicated, that's inefficient for your cache hit rate. So
that's why 50% probably is not a good idea at all, right? So you need to move this slider either to one side or to different side.
Exactly.
And I would prefer to move it to 80, 90, but it's risky.
I've seen more commonly people like starting to point to maybe closer to 40 at the higher end and like lower towards 10 at the lower end. But 80 or 90, it just sounds wild to me when you consider what else we want to use memory for it.
My personal experience, I spent like some time studying various cases and making a lot of experiments, trying to develop methodology, full automated methodology so each particular database we take workload. Somehow it's different topic, and we just run a lot of experiments and see where is our optimal point. Sometimes we have like local optimum before 50% and slightly better optimum after like we pass 50 and go to closer to 100, but again it's risky, we can discuss why. But eventually I got disappointed in this area completely, like absolutely disappointed, because query performance, things you do hits more. Like right now I prefer to say like let's just put 25%. We know probably we are not optimal, but we are on safe side, and let's first focus on different settings which are very influential and query optimization. And if we do need to squeeze a lot from performance, like for example we have 10,000 Postgres nodes and we need to save on memory, we need really optimal performance, then probably it would make sense to find better setting than 25%. But in my opinion, if you start with 25% for OLTP workloads and then say we are going to optimize it and say maybe 40 is better, you have premature optimization because most likely you have different things to tune first. And not to tune, but query, optimize workload, you lack indexes and so on. You need partitioning to have data locality, to use the buffer pool better, more efficiently. And if you focus on that areas, maybe when you return and think about 25 or 40%, which will probably give you 10% benefit, you think like later, and you keep 25% for longer. This is my current understanding of this topic. So again, like I would like to thank Henrietta Dobrovskaya. I always forget. I'm bad with names as usual, but I would like to thank her because it was like cold shower for me when I presented our approach for Postgres config tuning with experiments and so on in New York, some maybe 5 years ago, and she said like, you can optimize a lot, but then developers or ORMs write bad queries and all your optimization is vanished because queries lack indexes or written poorly or like and so on. And my experience was like, no, config optimization is super important. Let's do it. But then I switched completely, and now we work on query optimization as well with experiments and thing cloning and so on. The change happened there. So I say like shared buffers optimization is probably number 10 item you want to optimize.
Out of interest,
25% and go elsewhere first.
yeah. But given our topic is memory management,
Well, we have other memory settings we need to consider, and they are
Yes.
also very interesting. But shared buffers, of course, number one in terms of Postgres configuration, because it's hard to change, because restart is needed. And it's influential if you don't change it at all, because original Postgres default is 128 megabytes, right? And there is also different default dictated by apt or yum packages, which probably half of gigabyte, I don't remember, maybe 256. But these days we can use these settings on Raspberry Pi and also not on the latest models, because latest models have like 8 gigs of memory. So the default settings of shared buffers and Postgres config is so outdated that can be used only on teapots. So it's teapot Postgres style. So it should be always tuned, but 25% rule is good enough.
The one exception is that a lot of people these days, their default config is now the default config chosen by their cloud provider. So, and this is because of the reason you said.
Yeah.
This is one of the few settings that I see I've seen everyone I've checked has tuned this. Not always to people's taste, but this is one people.
And they use 25%. Right. Most of them.
All of them.
Not? What's your experience?
Well, I haven't checked all of them like recently and started new instances, but I was talking to a customer of Heroku just recently, and they're having a real ordeal trying.
Heroku is. It's not. It's very old solution.
Whoa. Yeah, but
It's
lots of people are still on it.
Okay. Yes, I know. I have customers as well. Yeah.
And they have tuned ShareBuffers. They have changed.
They don't have
ShareBuffers
PG repack even.
I know, but they have changed it, but not to 25%, which is interesting because that means it's a deliberate decision not going with what the docs say. Like, I think the easiest, the least
because
thoughtful
this
thing to
decision
change-
was made before it was written into docs.
Maybe.
So
good
probably probably they still apply 25, if not more than 8 gigs. And if it's maximum 8, so maximum of 8 gigabytes and 25%. And this was also a recommendation in old George Berkus PostgreSQL Conf annotated PostgreSQL Conf.
Annotated conf. Yeah.
It was, yes, and it's unfortunately quite like lagging for new versions, but 25% is current rule of thumb. That's it. Let's keep it. It should be number 10.
Cool.
Let's agree to
Wow.
put 25% and forget about it for a while.
Cool. What else?
So we have
what are we doing
25% went to shared buffers, and if we live in a vacuum, nothing else, and processors are not using memory, 75% will go to effective cache size, right? Oh no.
Yeah.
The
Weekends.
Sorry. It will
Operating
go
system.
to the patch cache, and we have effective cache size, which is additional but very important setting, which tells Postgres Planner how big are our both caches together. Not together. It's interesting.
The remaining.
Maximum
Normally people recommend setting effective cache size as
3/4.
the total memory minus or 3/4.
No, not
right?
not minus. It includes shared buffers. For example, if we indeed decided to exceed 50, it's also. I remember several years ago we discussed it at Hackers, and Bruce Momjan was also participating, and I think Bruce fixed it in documentation. I participated in that discussion. So, for example, if shared buffers is 60%, and we know our processes, backends, and other processes, non-Postgres processes, use, say, 10%, so we have 30% left for page cache. It means that, 60 shared buffers, 30 page cache, effective cache size should be either some of them wrong, right? Because we have duplicated caching. But so either maximum or some.
Sure.
It's interesting. In this case, I already forgot. But in general, like if we start with 25% for buffer pool, I would just put 75% for effective cache size as a starting point. But what I would like to say here, we can put 200, 500, 1000% of our RAM available. And since it's not allocation, Postgres will work. And this helps us on our environment where we don't have enough memory, but we want planner behave similar to production, actually exactly like production. We use planner settings and work mem the same as on production, and effective cache size is one of the most important planner settings. So we can full Postgres, and the planner doesn't look at real available RAM, real available CPU, disk, doesn't know about it anything. And doesn't look at shared buffers even. It just looks at effective cache size, and it's interesting.
I still remember your tweet about that. I think you did a poll, and I got it wrong. I thought it would take shared buffers into account in the planner, but I was wrong. So yeah, that was a few years ago now. But yeah, good one. I feel like we should move on. I feel like, from my experience at least, work mem is hugely important here. Is that the next thing you'd want to talk about, or where would you go next?
Yeah, so brief summary. Shared buffers is more like physical setting which will affect timing of query execution. Of course, if data is there, good. If it's not there, bad. So we need to inspect page cache again. And for Postgres, it already will count as buffer read, reading of buffer. But then it might be disk related, but maybe not without disk at all. So Postgres doesn't know. That's why we need pgstat kcache to understand. But effective cache size is for planner. How planner chooses. Planner thinks, okay, we have that much. We expect that many gigabytes of RAM involved into caching. So it's more optimistic that like it will be in memory, or it expects some data reads happening, so more heavy operations, I/O operations. So this is very like high level thing, like logical. Only planner decides what to do. But shared buffers is again, it will affect timing, but not behavior of buffer pool. We should mention our episode about checkpointer tuning because when some buffers are changed, and it can happen during select as well if hint bits are updated on the fly, and the buffer is like in virtual memory, it's a block read by from
page,
disk.
Yeah,
But it's page, yes, 8 kilobytes. We have huge pages as well, right? So it's a different topic. But buffer is 8 kilobytes, and if we changed at least something in it inside this page, it's considered as dirty, and then checkpointer or background writer first, then checkpointer, and sometimes backend itself. They need to clean it, so like synchronize with disk. So less stress will be next time we need to perform recovery. And we discussed this topic, right? So we need checkpointer tuning. But what we didn't discuss probably is that page cache also needs tuning sometimes, because if we accumulate a lot of dirty pages in page cache, it's not directly related to Postgres, but it's related to overall performance of our database. If we allow operational system to accumulate a lot of dirty pages in the underlying page cache, we might have performance issues as well, because we want this process to be like smoother, and probably you want to tune the behavior of page cache, adjusting with sysctl, adjusting kernel settings so page cache doesn't grow a lot, and the operational system flushes dirty buffers with ptflush and so on, like more often. So, but it's slightly outside of Postgres, but it's sometimes very affects how we work with memory. So again, Postgres relies on page cache a lot, so this topic should be studied as well. Okay, now what's left? Well, work mem, maintenance work mem, these two guys, first of all, right?
Yeah. And when you mentioned the previous episode, I thought you were actually going to mention the buffers episode, and I think there's also something to be said there before we move on, which is when you get when people are doing estimations for their cache hit rate, for example, or if you're looking at a single query plan with buffers, which hopefully you are, you'll see hits and reads, but though the thing you mentioned here that's relevant is that those reads aren't necessarily from disk, they could be from the OS page cache,
Right.
and we can't tell. So
Explain
yeah, something
cannot
to be
tell.
aware of.
Yes. And pgstat
Explain
statements
yeah.
cannot tell, but pgstat cache can.
Yes.
And unfortunately, we don't have anything for explain. It would be great to have some extension which would extend the explain analyze buffers, so we would see real disk I/O. But real disk I/O can be measured if you look at proc I/O for our process ID. You just cut /proc/IO process ID, and you see reads and writes, and this is real disk. So you can see it if you have access to Linux. Of course, not on RDS.
Yeah.
So sometimes you can cheat a little bit and check what's happening before you run explain analyze buffers and after it.
Nice.
Right.
Workmem. We have a
Workmem.
default of
Workmem. So Workmem, we discussed it briefly recently as well. So the difficulty with Workmem, nobody knows how much we will need in advance. And each query can consume multiple times of Workmem, but sometimes only fraction of Workmem. So Workmem, this defines the amount of memory each backend needs to process query for operations like hash join, ordering, and grouping, and so on. And if we have multiple of such operations for one query, we might use multiple times of Workmem. And if we reach Workmem and we need more, then temporary files will be created and query execution will slow down significantly.
And that's because Postgres is no longer doing, for example, that sort in memory. It's doing that sort on disk using a different. Yeah, exactly. And it's not. Yeah, it's not even just per operation, but it can. If we did an episode recently on parallelism, it can be per backend per operation, so it can multiply out quickly.
Yeah. Also, there is some setting for hash multiply. Yeah. So it's very tricky to understand how much memory you will expect. And usually our approach for tuning is very reactive. Of course, default for Max again is for teapots only, usually. Yeah. But it's very related to max connections and how many CPUs and how many connections for backends you expect. Starting from Postgres 14, we might allow a lot of idle connections. And you mentioned Andres Freud a couple of tweets and a couple of blog posts related to memory consumption by backends and also max connections, and is it okay to have a lot of idle connections? Starting from Postgres 14, we have optimization. It's not related, it's not like memory. It turned out that memory management was not number one problem. Number one problem was how work with snapshots is organized. So these are very good in-depth blog posts, these two. But the key to understand the key right now is we cannot say this process. It's very tricky to understand how much memory is used, first of all, by process. Even if you have all accesses and you see PAS top, everything, you have SAR, all of things, but it's hard to understand in Linux how much memory is really consumed by each process. But also we cannot limit it reliably. We cannot say, okay, 100 megabytes for each backend, that's it. Unfortunately, because if we say Workmem 100 megabytes, still backend is allowed to use it multiple times because of this behavior. Workmem defines the limit for each operation, not for backend. And also we have parallel workers. So together this becomes quite tricky topic, and our approach usually is very reactive and iterative. So we first start from some safe Workmem setting. Safe approach is okay, we have max connections, say 300 or 500 for our 96 or 244 core server, big one. And then we say, okay, we should be on safe side. We know 25% is shared buffers. We know some backends will have maintenance Workmem to be used for index creation or auto vacuum. And we allocated 4 gigs or 2 gigs. We can discuss this also. We should discuss this. And we also have maximum 10 workers of 40 gigs. we have like maybe half of terabyte, 700 gigs. So 25% there, 40 gigs for maintenance workers like index creation, reindex, index maintenance, because it's needed all the time. And auto vacuum, like we have 10 workers auto vacuum, 1 or 2 workers rebuilding indexes. Okay, we know math is good here. So what's left? We have, ignoring page cache, we have like 300 gigs, for example. For a while, we ignore page cache and we say, okay, we have 300 max connections, 300 gigs. It means like we can give up to 1 gigabyte to all backends, right? Okay, that's good. So let's have some multiplier, 2 or 3, because we know some queries can have multiple operations like sort or hash join and so, like hashing and so on. In this case, we say, okay, our quite safe setting is 100 megabytes times 2, 3, it will be 200, 300 megabytes. We don't reach 100 gigs. Oh, we don't reach 1 gigabyte per backend. It means we can use 100 megabytes for WorkMem. Let's start with it. And we start with it, and we see most backends don't reach it even once. We can see it like based on, but some backends exceed it. They need more, and this is imbalance. And we also see page cache is quite huge. Like what's left, it's most page cache. We understand. Okay, our average WorkMem consumption for WorkMem is quite low, but sometimes we need more, and so we start to raise it. We know on average we don't reach it at all, but some backends need it. We can have 2 options here: either to set locally in sessions. If we control application code, we can say set WorkMem right for particular query because we know it's very heavy and we don't want this query to use temporary files. Or we can just raise WorkMem globally. We observing our workload for quite long time. We see it's quite safe, and it's not uncommon to see that people are having settings not safe already. If you take max connections, take WorkMem, have multiplier 2 or 3, and consider shared buffers and maintenance WorkMem, you see that we don't have so much memory. But we know we don't reach the limits.
And this is what I was alluding to at the beginning of the episode. You say it's not safe, but you mean it's not safe in theory, not safe in practice.
For particular,
and that's a very different. Yeah, exactly. With the current workload. So it's an interesting topic. I think what you said there is actually really interesting. Like, I think that's a really good point that sometimes gets missed, is it can be set at different levels. And you can, if you've got one reporting query that runs once a month, for example, you could set a higher number for that.
Gigabyte, 5 gigabytes. Yeah, just
especially if you know it's
single
running,
backend.
Yeah, if you know it's running at a time that's relatively quiet, for example, and it's not going to be contending with lots of other things. So lots of things are possible here. Smaller servers than the ones Nikolai are talking about are available. But even for very small services, even for extremely small instances, I very rarely see one where a setting less than 16 megabytes or 4 times the default is ever sensible as far as I've seen. So, and quite often even these small queries, even these transactional workloads do spill over 4 meg. Like if you start logging temporary files, which is very good. I think it's very good advice. Although I saw in one of the AWS docs that you shared with me that I'll link up, that they advise only turning it on temporarily. So I was going to ask you if that was the case for you as well. But logging temporary files is extremely useful. And if you see lots of ones being logged in the 4 to 10 megabyte range, it's not uncommon for transactional workloads. You've probably not changed the setting, and it's well worth looking at.
And we have aggregated statistics for temporary files, the size and number of files occurred in PGStat database for each database. So this is a good thing to monitor as well and have alerts and so on. But as for logging, I prefer logging all temporary files occurrences in tuned server. If it's not tuned and each query execution involves it, it will be disaster. But normally we already raised shared buffers, raised WorkMem, and since we raised WorkMem, only particular queries are experiencing temporary files. So it's okay to log them all. So I mean to set 0 as threshold of size to be logged.
But I would say I see issues with workmem way more often than I see issues with shared buffers, probably because of my
Right.
bias, but also because cloud providers don't tend to tune it. But because it's this scary
It's
setting,
dangerous.
they don't even use that formula you were talking about. That formula that shared lots of places. I particularly like an EDB guide by Vic Fearing. I'll share in the links as well. But that formula, they could apply it, right? They could set a sensible setting.
Annotated PostgreSconf also has it. This is
But my
safe
experience is they
starting
don't.
point.
They start at 4 megabytes still, even in, yeah, well, so maybe I'm wrong, maybe I'm a bit out of date, but a lot of them that I was checking didn't.
And you
didn't
see
change that.
temporary files and plans a lot, right? And first advice, raise workman.
Yeah.
Because
Or first advice,
I
first
often
advice,
see
check your
Formex.
indexes.
Check your indexes. Well,
Well, first advice, tune the query. Like if you're doing a massive sort
Yeah.
and like, you know, like it,
in this case, second advice, apply partitioning.
well, first
and
advice, do
optimize-
less. Yeah. Try and avoid the sort. Try and avoid the
First
hash.
advice is always buffers. Because if you focus on buffers, you like database is all database performance optimization is about to do less I/O, right? And that's the key for good latencies, timings, and so on. Less I/O.
This is well, we're possibly talking about the one exception to that in this today's topic, which is memory, right? Like it's not reporting buffers when if we're doing like a sort in memory. Is that I/O? I think no, but like,
It's still I/O. I/O can be like internal memory or external memory. Disk
Okay.
or page cache considered as external, but let's forget about it.
It's not reported as buffers, crucially, if it's done in memory. So that's but like maybe that's a implementation detail.
Right.
Regardless, check, like if you do one thing as a result of this episode, please check what your current work mem setting is, and if it's 4 megabytes, I'd start checking your
Probably your cloud provider already tuned shared buffers not to optimal state but good enough state, but workmem probably they didn't touch it. It's still 4 megs, and for modern workloads and data volumes it's tiny size, and also like teapot size and so on. But if you raise it a lot and max connections is huge, a lot of idle connections, probably you will be out of memory, so it should be also done carefully in maybe multiple steps, observing and so on. And also, but again, like I agree with you, query tuning and partitioning is also important here because it gives data locality. And you mentioned when our database can be put fully to shared buffers. That's great. But if we partitioned, we can say, okay, this is our total database size, but this is our work set size. Only fresh partitions we are work intensively with. And buffer pool has and page cache, they both have quite good simple mechanisms to understand what's needed, what's not. So like usage counters and so on, and it can be studied using good extension called PG Buffer Cache. You can study what's inside your buffer pool right now. It doesn't hurt to run it. It will take some time because it will scan whole buffer pool. If it's huge, it will take some time, but it will give you statistics like this relation, this index is present by these like blocks, and you can aggregate it and the documentation. It's official contrib module shipped with Postgres contrib modules, and the documentation has basic examples, and you can understand what's inside the buffer pool right now. And this is interesting. So if you apply partitioning, these things might start improving because instead of mixing all the new data in single table and indexes also, it will start improving a lot.
Yeah. In fact, like this is one of the...
more efficient. It will be more efficient.
Timescale give this recommendation in their docs, I think. So they actually talk about setting the chunk interval so that at least your latest chunk, which is their word for partition, fits in shared buffers. So that's another way of thinking about it. Like you could be choosing your partition's like size or frequency based on what you have available in memory-wise. So it's a cool flip way of like thinking about it.
Yeah.
You said you wanted to talk about something. I've forgotten what it was, but we needed to make sure we
Maintenance
covered
work
one more thing. Yes. Well, yeah. Let's cover that.
So to vacuum work mem is set to -0, meaning that it's inherited from maintenance work mem.
Minus
By
what?
default. -1.
Yeah.
Auto vacuum work mem is -1 by default. In most cases, I see people don't touch it. So it means that maintenance work mem is both about index creation and such operations like index creation or indexing, and also auto vacuuming. And usually, I don't remember default, it's also very low. Usually you want to raise it at least like 1 gigabyte if you have a lot of memory, or half of a gigabyte. But interesting, like I made a couple of years ago, I made new experiments trying to understand how beneficial it is to go to higher values. And for index creation particularly, I didn't see big benefits after half of or 1 gigabyte. Difference between 1 gigabyte and 5 gigabytes in my experiments were low. It was low. So, but don't trust me blindly. It's good to experiment always, right? So you can just create your index. You create your index with one setting, then you restart server to flush the state of shared buffers and everything. And also don't forget to flush page cache. You say echo 3 to some page cache. You can find it in the internet, how to flush page cache. In Linux, it's easy. It's just single line. And then you start experiment from scratch again with higher value of maintenance work mem. And you compare duration, for example. And you can compare how much I/O happened, for example, and so on. It's a good experiment to run in simple exercise, and you will see is it beneficial to raise it for your particular Postgres version of your database and your indexes and so on. For auto vacuum, I think it makes more sense to raise it, but again, you can experiment and vacuum, but you need to have dead tuples in some same number of dead tuples for each experiment run. So it's interesting how to build this experiment. But again, like if our listeners have different experience, please comment anywhere on Twitter, YouTube, anywhere. I would like to hear if some of you had found beneficial for index maintenance to raise maintenance work mem much more than 1 gigabyte, for example. But so since auto vacuum work mem is set to -1, we need to take maintenance work mem, because it's used by auto vacuum workers, multiply by auto vacuum workers, and my recommendation is 3 is not enough. Usually, if you have a lot of cores, raise it to like 25%, for example, of cores available. And then you can understand how much memory can be consumed by auto vacuum workers as well, right? So
and the limit
can be a lot.
The limit is per worker, right? The limit we talked about earlier. Each worker can consume that. So
exactly.
But only once, right? Not multiple times. It's not like
only once in this case, as I understand. So my preference is more, especially if we have partition case, a lot of partitions, and so on. In my preference is more workers, and maybe not so big maintenance work mem. And index maintenance maybe just single backend recreating indexes. Maybe sometimes 2, maybe 3, but not many.
Nice. I feel like we should wrap up.
Right. Yeah.
I feel like we should wrap up soon, but I do want to there's a few links that I found really useful. One in particular we haven't managed to mention yet. So maybe we should do a quick, what's it called? Like a quick fire round of good resources.
Yeah, we first of all, both internals books or online books. One is PDF, one is just website. They're interesting, from Suzuki and from Rogov, and they cover this many aspects quite deeply. So if you want to go inside, I think in this case almost everyone should go inside, and even backend developers could benefit from understanding how Postgres works, like process model, no threads, shared buffers, always to work with any relations, and so on. Work mem, maintenance work mem. This is the number one thing.
Yeah, before you move on, I wanted to give a special shout out to the Rogov book. I was expecting, given it's translated, for it not to be as clear and well written as it is. And I looked up just before this who translated it, and that's Lyudmila Mantrova. So shout out to them because it's fantastically well written, even the English version. So I'll share a link to that.
Yeah, I use this book as a reference, and I actually honestly don't realize which language I use because I speak both, and I found both versions are good enough. It means that translation is really good. I agree. So, but before the internals, we should mention documentation, of course, and also README file in backend. I don't remember
in the source code.
Yeah, but about buffer pool, because it's quite well also plain English, explaining some details how buffer pool is organized and about pins and so on, about logs. But also interesting for folks who are using newer versions of Postgres. In Postgres 14, we have PG backend memory context. A system view which gives aggregated stats for memory usage. I never use it in production somehow because I still have mostly older version. Well, somewhere already Postgres 14, but I need to have some probably incidents to start using it. It's interesting thing to keep in mind that now we have good observability tool. And in Postgres 16, pgstat.io is added.
Coming soon,
Right, also aggregated statistics for how buffer pool, how many operations happened, timing, and so on. Yeah, also very interesting. So, and PG buffer cache. These are things like our quite deep, like this is enough to go quite deep. And also PG pre-warm, by the way. If you want to restore the state of buffer pool, you can check PG buffer cache plus PG pre-warm, and there's also automatic pre-warming starting a couple of years ago, some versions ago. There is a recipe. So you have restart, you want to restore the state of the buffer pool, so query performance is good again. It's also possible. I never used it, honestly, but I know this is possible, so knowing which is possible also sometimes is important. More important than knowing some details sometimes, right?
I've heard people using it for experimentation, but not for other things.
Mm-hmm. Yeah, this is an opposite approach. Instead of starting cold, you probably want to start from the same warmed up state. Makes sense. Yeah, and also worth mentioning that if you are on ZFS and you use, for example, Database Lab, you can use ZFS on production. And in this case, you have branched Postgres. You can use smaller buffer pool. Of course, in this case, the cache is not so smart as the buffer pool, but it's good to have multiple Postgres versions, like branched Postgres versions, utilizing single underlying cache instead of regular page cache. It's called Arc, ZFS Arc, and if like all databases are writable, running on single host, but they use single cache. ARC from ZFS. And it's great to see that shared blocks are cached there. So you start new branch and you're already quite fast. It's not in the buffer pool, and we need to use smaller buffer pool if we run multiple Postgres on single machine. But it's already quite fast because it's cached in this underlying ARC. So it's also interesting approach, quite underappreciated, I think. But some folks run ZFS on production, and it's interesting. So, yeah.
Right. I think that's enough for today. What do you reckon?
Right. Yeah, that's it. And I like your idea, raise work mem as a single recommendation. Consider raising it, but be careful.
Yeah, exactly. In fact, I've got a blog post on that. Can't believe I forgot to say. But I'll share that as well.
Good.
Right. Thanks so much, Nikolai. And I won't see you next week. Because even though last week we were talking about such a good streak of weeks in a row, I'll be missing the next two.
Yeah, so, it's called Slacker, right?
Yeah, absolutely.
But we will have episodes, no matter what.
Wonderful. Well, I look forward to coming back from my holiday and seeing what they're on and being a listener.
Right. Surprise. Good.
Yeah, exciting.
Okay. Thank you.
Take care and catch you soon.
Bye.
Bye.